Let's look at the details of the surface geostrophic currents then. Remembering our diagram again, we derived the pressure at height z near the surface by assuming that the sigma variations are small compared to the sea level variations, and the expression was Pz, z is this one, near the surface. Just have to decide how near is near. Ps minus g rho ref times z minus eta. So how does the pressure vary in the atmosphere? We had already seen that, exponential in the vertical as opposed to the ocean, which is almost linear. Sea level here, just to confirm what I said before, here is the surface of the Earth. Remember, we keep saying Earth is a sphere, but over geologic times, because it's not a solid block of rock, it has adjusted into this ellipsoid that we looked at. It's squished at the poles and bulging at the equator by a couple of tenths of kilometers. And the geoid, as we said, is basically approximates the mean sea level. How do you estimate it? You basically assume you turned off the winds and the tides, as I said before, and you estimate it mathematically, and obviously it's an approximation. But sea level is referenced with respect to the geoid. Why do we do that? Because with reference to the ellipsoid, the geoid can vary by tenths and even 100 meter in places. So you can see that geoid is lower than the ellipsoid, reference ellipsoid here, somewhat higher here, and these calculations are also run through the land. We won't go into the details, but this is very critical. Estimating the geoid is very critical to estimate sea levels from altimeter, because altimeter doesn't give you sea level with respect to geoid. You have to estimate the geoid and remove it from the sea level to get accurate sea level measurements. Going to geostrophy and thermal winds, we had written before when we approximated rho ref rho as rho ref plus sigma, and then we had assumed sigma is a function of temperature, and we had related these gradients to temperature, and that's why we call them thermal winds. But the main point was horizontal gradients of density were giving us vertical shears of geostrophic winds. So geostrophic wind shear was dug dz and dvg dz, and that was equal to g or f rho f times d sigma dy in the x and minus d sigma dx in the y. Okay, we used the standard methodologies to derive these. You can go back and look at the podcast. In the vector form, we had written the geostrophic shear as minus g or f rho f z hat cross grad sigma. So we are still in the z coordinate, and z hat is the unit vector in the z direction. In that case, for the ocean, if we use the same expression and look at the horizontal gradients in the sigma and the typical depth of the water column that we are interested in, and the variation over the horizontal scales of L, we get currents of the order of 8 centimeter per second at a particular location where these values were picked off from the sigma charts. And this is fairly accurate. Just to say that the surface currents are actually, it's just below the surface, because at the surface you have wind and friction. Geostrophy means no friction. Okay, so it's kind of funny that winds use friction to create bulges in sea level, and then sea level gradients give us geostrophic winds just below the surface. Okay, so geostrophy works. Ocean is in geostrophic balance at large scales. Obviously, there is an F in the denominator, which means near the equator this is going to fall apart, right? This is what we have already said. Looking again at this potential density anomaly sigma rho minus rho f, I think I mentioned already the numbers in the 20s are essentially the deviation from the density of 1,000. So when you add salinity and temperature effects, you get sigma of in the 20s. Okay, as sigma gets larger, density gets heavier, so as you go to the deeper ocean, sigma increases. This is looking at the top 1 kilometer to highlight the structure of the subtropical gyres, upwelling regions, and so on. You can see the meridional contrast, the deep water formation here in the North Atlantic region, even though this is averaged out. And if you look from the surface to the bottom, about 6 kilometer, you see that bottom of the ocean remains fairly uniform, as we have seen, and the entire seasonal variability happens just in this top 1 kilometer or so, except here where the dense waters from the surface can sink to the bottom, or here the same thing happens. We will see that later on. Okay, so the horizontal gradients of sigma here can give us geostrophic currents which approximately match the measured currents that we saw before. Starting with our hydrostatic balance again and looking at our cartoon schematic of the height of the sea level, free surface, and near surface Z versus deeper Z, we want to now look at what happens to geostrophic currents in terms of eta. Okay, so start with that. We wrote Pz as Ps plus Z to eta G rho dz equals Ps plus G angular bracket rho times eta minus Z. What did we do? Obviously we have gone from Z equals Z0, we have gone to this level where variations of sigma cannot be ignored anymore. Here we ignored the variations of sigma near the surface, but we cannot do that anymore. So what we did was split this integral and take out rho as a height weighted density, which is defined as this. The angular bracket rho is basically 1 over eta minus Z, Z to eta G rho dz, which allows us to excuse me, that allows us to write this in terms of eta minus Z. Okay, so we can then write geostrophic currents for below the surface, away from the surface, where sigma variations are not negligible anymore. So compare that to P0, PZ0, which was near the surface, where we had ignored sigma variations, so we had just got PS plus G rho ref times eta minus Z0, whereas here we have G times this average density of the water column. Okay, simple. So we want to write obviously dp dx and dp dy to get our geostrophic currents, which become for the surface G rho ref d eta dx d eta dy. So if you measured sea level variations from satellite altimeter, then you can derive surface geostrophic currents. Looking at our expression for geostrophic winds in the atmosphere, or the general expression we had derived, geostrophic surface currents then are just given by this relation here. Okay, we're just plugging in the relations from here. Okay, so measuring sea level gradients gives us geostrophic currents near the surface. In the vector form, obviously it is written as UG surface equal G over F Z hat cross grad eta. We will see that the deeper ocean does something funky, and that's kind of the cute thing about the ocean. Basically, it comes down to what we said before, that the deep ocean has no motion. It's basically so slow, few kilometers per year, that you cannot measure the currents directly. You have to use tracers and other methods to do that. So how does the ocean accomplish near zero currents at the bottom if there are density gradients. We will see that the pressure gradient compensation happens between the sea level and sigma surfaces.